All engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to the programme where we bring you the latest breakthroughs in science, technology and medicine with me, Chris Smith, and with Harry Lewis.
This week, a COVID sensor that clips onto your lapel and fish that can drive. I bet they're having a whale of a time.
Don't go there. Also, the roles that robots are increasingly playing in our lives. We're going to get a look at one of the world's most advanced surgical robots, talk to the team behind Boatim at Boatface that's going to explore under the Antarctic ice, and we meet a robotic musician you've never heard Twinkle Twinkle Little Star sound so good.
The Naked Scientists podcast is powered by ukfast.co.uk.
But first, with COVID hogging the headlines, what would under normal circumstances be a big story has been flying very much under the radar, and that's bird flu. Europe is currently witnessing an outbreak on a massive scale, and the UK is involved too.
The cause is the H5N1 strain of the influenza virus, which doesn't, at the moment, spread well among humans. But the situation's alarming because the virus could adapt to us and begin to spread, possibly triggering a parallel pandemic alongside COVID. Perish the thought. But there's another aspect to this, which is why these viral outbreaks are happening now. And are we doing enough to stop them? Do we need, for instance, to up our surveillance game? Christine Middlebiss is the UK's Chief Veterinary Officer.
In the UK and across Europe, we are seeing the greatest number of bird flu outbreaks in kept birds that we've ever seen before. In the UK, we have 79 confirmed infected premises. Italy is having a lot of outbreaks. They're at nearly 300. Hungary, the Netherlands, France and Ireland. And that's because there's an overwhelming level of infection in the migrating wild birds that have come back to us for the winter. And they're bringing infection, and that's getting into our own kept birds.
And what sort of flu are we talking about?
Bird flu, mostly specific to birds. There have globally been a few reported cases, mostly in Asia, of infected people. We did sadly have one person infected in the UK, but he's been quite well in himself. But he had very close living circumstances with his own birds. So very low risk to people, but it's very nasty in birds, and particularly some types of birds. So chickens and turkeys particularly, it's fatal for them, and that's why we want to control it.
Apart from the obvious economic impact and possibly food supply impact, is there a human risk down the track, though, in the sense that obviously if you've got a type of flu and it can jump the species barrier, could it either turn itself into a form that's better at spreading among people, or could it mix up with human seasonal flu and produce a sort of hybrid, which is the worst of both?
What we're seeing so far is that the genetics of this virus are very clearly linked for birds, but it's important that we all keep checking because, as we know, viruses can change. And that's why routine hygiene precautions for people, all those things we've become really familiar with in the last 2 years. Wash your hands every time after you've handled your birds. Don't handle dead or sick birds. Those things are really important so that the virus doesn't get an opportunity to think about changing.
Why is this year so bad?
Because of the overwhelming level of infection in the migratory wild birds. The flight pathway that the birds that come to us are on, they go back to the north of Russia in the summer. And that's where a number of different flight pathways all meet up. So birds that are covering different parts of the world, and they exchange their viruses and things there. And so then when they come back to us in the winter, they might be bringing different or slightly changed strains. Why we're seeing it this year when we had an outbreak last year, because usually we expect to have 2 or 3 year quiet years, we're not sure, and it's something we're looking really closely at because we want to think about what might happen next winter and the winter after that.
Does it teach us anything, though, about what we need to do by way of surveillance for these sorts of infectious diseases in future? Because one of the things people keep saying is it's unfortunate that we weren't better prepared for what happened with COVID. Do we need better surveillance to include things like animal viruses like bird flu?
So we actually have good surveillance, particularly for the things we know about. I have a team that every day that look around the world for any changes in animal disease and animal health status. And then we translate that into what might it mean for the UK for diseases, ones we call zoonotic, that can spread from animals to people. We share that with our public health colleagues. So we're really joined up in that space. But what I think we can do more of is working internationally about sharing information on new and emerging things, the kind of known unknowns and unknown unknowns, so that when generally internationally somebody somewhere spots something different, that there's a kind of pathway and route and mechanism where they can share that information so that policy makers around the world can be better informed and prepared quicker.
Because all that sounds absolutely terrific, but we missed COVID, didn't we? Which I know the jury's out on exactly where it came from, and still people are debating about whether this is a laboratory experiment that got away or whether it really does have a genuine wildlife origin. But the endpoint has been the same: dramatic spread and loss of human life. A lot of these sorts of diseases do have their direct origins in animals, don't they? So monitoring like the type you're describing is absolutely critical to keeping the lid on infections in the future. So I'm just wondering how many more we might have to miss because we missed this one.
I wouldn't necessarily say we missed this one, because trying to do surveillance of all the different world's animal populations in a systematic way that would be valid enough to give you an indication, I think we have to be realistic, as particularly when it's wildlife that might be concerned, is pretty impossible. It would be really, really difficult. So we have to understand where their interactions with other animals or people happen and monitor at those spots. That's what I was meaning about sharing information internationally in a more coordinated way. People are monitoring those connection spots and things, but we could do it more systematically and in a more of a coordinated way. Working, the concept of what we call One Health, which is human, animal and environment health all coming together. And we're quite good now at the animal and human bit, but we need to build on having more of the environment in it so that we understand if we change something in the environment or it changes of its own accord, we're thinking what might be the impact for animals and what might be the impact for humans.
What indeed. Christine Middlemiss, UK Chief Vet there.
Now, from current affairs to something that's making history eventually, I suppose you could say, after millions of years. Mark Evans, Geological Laboratories and Collections Manager with the British Antarctic Survey and team leader of a rather interesting expedition, joins Harry Lewis to spill the beans on what's turned up in Rutland, the UK's smallest county.
I guess it all started actually in January last year. I had an email from a colleague of mine at University of Leicester who'd been sent some interesting pictures on email, and they seemed to show some large bones, I guess, sticking out of mud. And that's pretty much all we knew. And Dean and I looked and we thought we knew what it was, but we weren't entirely sure. Because I live locally, I'm only about 25 minutes from where the thing was found. So I decided that I would go and have a look. So I met up with a guy called Joe Davis, who manages the nature reserve at Rutland Water. And Rutland Water is the largest artificial lake in the country. And Joe took us out to an island on a lagoon, which is part of the nature reserve at Rutland Water. And there he showed us what he'd found just on the edge of the water. It was very, very wet, very sloppy mud. But there's enough there to confirm what Dean and I had thought we could see in the photographs, that this was part of the skeleton of a large ichthyosaur.
Mark, on this preliminary little survey that you had, how much of the bone do you need to see to get that idea that you know what this dig might comprise of?
With ichthyosaurs, the vertebrae are quite a distinctive shape. They're almost like hockey pucks. And again, if you can see them at the right angle, depending how they're exposed, then they have distinctive articulations for the ribs. It was, definitely a large ichthyosaur, but at that time we didn't know quite how big this thing was.
And is there a range in the size or length of these creatures?
The smallest ones were less than a metre, and the largest we know of from good remains is probably about 21 or so metres, something like that. But also there are isolated fragmentary remains which suggest that they might have got larger than that, so maybe 25, 6, 7 metres maybe, which is approaching the size of large living whales.
Mark, you better put us out of our misery. What actually is an ichthyosaur?
Well, ichthyosaurs are superficially fish or dolphin or shark-shaped marine reptiles, and they lived in the Jurassic and Cretaceous periods, so between about 250 million years ago and about 90 million years ago when they all became extinct. This is a common misconception that they're some kind of dinosaur, but they're not. They're unrelated to dinosaurs. They just happen to live at the same time as dinosaurs, but all ichthyosaurs lived in the sea as far as we can tell. They had a dorsal fin, most of them, like a shark or whale or dolphin. They had a tail fin, which was vertical, and they had two sets of flippers. So they had front flippers and hind flippers.
What happens now? What point are we at with this preservation, and what does it mean going forward? What can we learn from it?
I guess the end point of the excavation was when all the big parts of the skeleton were encased in plaster jackets and then lifted with a great big telehandler, basically a forklift truck-like thing with a extending arm. And the skull and the surrounding matrix, the clay, and the supporting frame and the plasterwork weighs about a ton. And the abdomen, the body section, that weighs about 1.5 tons. So there's a big job to be done for those to be cleaned, for the matrix to be removed, and that's when we can start doing that part of the science on the rest of the specimen. So often you only get the head or bits of the body preserved, and here we've got the whole thing, literally all the way down to the tiniest bones at the end of the tail, which is the size of a penny. When it's cleaned up fully, we'll have hopefully some really great details of the bones to look at, which will give us extra detail on these animals, but also help us to work out this sort of diversity of animals back at this time, 180 or so million years ago in Rutland. But it's going to be a big job.
And at 10 metres, this ichthyosaur is the largest ever recorded in the UK. Quite a feat. Thanks very much there to Mark Evans.
From baffling British weather
The sideways spines of the vertebrae coming off here.
to looking at a cheetah from the inside out, games making their way to the clinic, and what to eat in your garden. The Naked Scientists In Short podcasts bring you a top-up of short, compelling science stories. Listen and download for free at nakedscientist.com/short or subscribe to Naked Specials wherever you get your podcasts.
Meanwhile, still to come in this hour, the adventures of Boaty McBoatface and robots that run on food and drink, just like you and me do. You heard it here first.
Now, though, people who work with radiation often don a device called a dosimeter that records their levels of exposure to make sure that they're within safe limits. But nothing has existed on a portable scale to spot the infections you might have encountered as you go about your business until now. Yale researcher Crystal Pollitt has come up with a cheap clip-on sensor that can alert the wearer that they've been through a coronavirus hotspot. At the moment, it needs to go off to the lab to be read, but in the future, an automated version, as well as one that can detect a range of other important infections, could be on the cards. She told Trisha Smith how it works.
The clip that we've developed to monitor airborne SARS-CoV-2 is a small wearable device that you can attach to your collar or anywhere else on your body. It has an opening in the shape of a Y that allows droplets and aerosol to then attach onto a polymer film called polydimethylsiloxane. And the original motivation for use of this was we were using this clip to measure chemicals. And this polymer is great at taking up many environmental chemicals that we're commonly exposed to.
And then when you collect that sample, it's then taken to a lab to be analysed?
So after someone's worn the clip, we have these aerosols and droplets that are collected on the polymer film. The clip's then sent to a lab, and we use PCR to then measure the number of SARS-CoV-2 copies that are being collected on the clip.
The device itself, is it completely reusable, or is there a component there that is one use and then you have to throw it away?
So the entire clip itself is reusable. The only component that we have to replace is the polymer film, which we fabricate in the lab and is pretty simple to get in there between times people wear it.
How are you developing the air sampler now? What else are you looking to use it for?
We're all hopeful that SARS-CoV-2 and coronavirus are going to be something that are not going to be a dominant focus of our lives, but we'll have to learn to live with it as cases continue. But there's also a number of other respiratory viruses that are commonly present, and that's what we've expanded to start thinking about. We've been looking at influenza as well as rhinovirus and other pathogens.
People can be actively shedding a dead version of the virus after they've had COVID, right? And that dead virus, inactive virus, is not dangerous in terms of people getting COVID from it. Can you distinguish between live and inactive versions of COVID?
We are only measuring total RNA copies of SARS-CoV-2. Now, if we wanted to look at the viability of those RNA copies, we could, because we are using this passive surface. We have just deposition of those aerosols and droplets on the surface of the film. But that's not something that we're currently doing, but it's a natural extension that we could go into.
What do you think are the applications for this wearable sensor?
We're not waiting to see is someone infected and having them to take a nasal swab, but we can see what is the potential exposure of any number of people within that indoor space that could have had a contact exposure. If you placed in a classroom, and then that could be indicative of what the teacher as well as all the students may have been exposed to for that period.
Crystal Pollitt, and you can read more about her new air sampler in the journal Environmental Science and Technology Letters.
Into the marine realm now, and to fish, and a new study that's made something of a splash online with a video showing a goldfish driving a tank around on wheels. Now, thankfully, this is not a military tank, but nevertheless, the fish guides its motorised home across the screen by swimming. Julia Ravi spoke to Ohad Ben-Shaka and Ronen Sergev from the Ben-Gurion University of Negev to get more details about this koi racer.
Call me strange, but I find driving a car to be really relaxing. It gives me a focus with a bit of peace and quiet. But in the future, maybe we won't be driving anymore. Various tech giants are beavering away trying to perfect automated vehicles. But what they maybe haven't considered in their grand plans is goldfish. I was scrolling on Twitter and one of the most bizarre yet fascinating videos popped up in my feed of a goldfish steering a tank on wheels with surprisingly good accuracy. And this was all in the name of science. I reached out to Ohad Ben-Shaka, a researcher behind this work, to see if carp pools could be what the future of driving has in store.
Julia, you might find it shocking, but fish don't drive cars. Trying to make them do so, even though it sounds cool, was not our end goal. In fact, making fish drive a robotic vehicle is part of our broader agenda to explore how animals represent the surrounding space in their brain and how they make navigational decisions.
Ohad and fellow researcher Ronen Sergev wanted to get the goldfish on the road to test their navigational skills. But as Ronen explains, there is one problem with wanting to teach a fish to drive.
Okay, clearly you cannot ask a fish to do that. So you need to train it in stepwise manner.
So the researchers used their powers of persuasion to get the fish behind the wheel, a target and some fish food. The goldfish were placed in a special robotic tank on wheels, which moves according to where the fish swims. When the fish tank hit the target on the wall, the goldfish would be given a treat, teaching them that this target was one to chase.
After training, which is usually 10 to 15 sessions, each one of them 30 minutes in total, they actually manage to go directly towards the target in order to consume as much as food pellets as they can during the 30-minute session.
And it seems the goldfish were specifically eyeing up the target. They managed to seek it out, even when the researchers were being a little bit fishy.
One thing to do is to take the target and place it on the other side of the room. So initially what you see is that the fish is going to the previous location, but then it actually finds out that the target has moved and it goes directly to the target. So this thing that we do in the experiment and we actually manipulate the arena where the fish needs to navigate actually make us believe, and actually it's very convincing, that the fish indeed control the vehicle, manage to drive the vehicle, and also remember the surrounding and navigate towards the target.
Do we think fish use this type of navigation, so remembering landmarks or cues, in the wild?
Visual landmarks must play a role in their navigational decisions, just as it helps us humans. But I want to be slightly careful here. We currently studied only goldfish, so at the moment we can't really generalize to all species of fish, but studying other species is indeed part of our plan in the near future.
Ronen and Ohad want to go further than just looking at the goldfish's movements in this somewhat bizarre driving scenario, but also to peek into their brains when they navigate in open waters.
What we ourselves currently develop is the ability to record the activity of single cells in the fish brain while it is behaving completely naturally in its environment. But this way we hope to find the links, if you will, between behavior and the neural coding, and hopefully understand how navigation decisions are indeed represented and made in the fish brain.
The results from this experiment, to me, it seems like goldfish are pretty sophisticated if they can do this type of navigation. Should we all stop using the phrase, "you have a memory like a goldfish," when someone's a little bit forgetful?
Yes, of course. As someone who works on fish for many years, these animals are amazing. They constitute something like 35,000 different species, and they do amazing things. So definitely we should stop thinking that fish have low cognitive capabilities or something like that. They just live in a very different world than us, and they solve different things differently.
But we've got no chance of water-mated vehicles coming along anytime soon.
No, I don't think so.
So if you hear the sound of vroom vroom coming from a river near you, you know there's a motor pike in the near vicinity. Julia Rovey was reporting on that study published in Behavioural Brain Research.
Much has changed for business owners, managers and staff recently. But with over 30 years' experience in telecommunications, award-winning independent company Spitfire have the expertise to make sure you stay ahead and can keep on innovating. Whether it's connectivity, MPLS networks, firewalls or phone systems, Spitfire can help. To find out more, go to spitfire.co.uk. That's spitfire.co.uk. Spitfire, telecoms and IP engineering solutions for business since 1988.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
You're with your favourite science show. That's, of course, The Naked Scientist with me, Harry Lewis, and Chris Smith. For the rest of the show, we're talking robotics. Tricia Smith has been on the lookout for how robots are helping us to go places we can't go, do things we can't do, and help us in our day-to-day lives. Over to you, Trish.
Do you recognise this one? This is Beethoven's 1801 Piano Sonata No. 14, a musical piece written for a solo piano and one of his most popular compositions. The pianists among you will know that what really brings sheet music to life is tempo and force, how you play with the timing and softness of the notes to convey emotion. What's this got to do with robots, you ask? Well, engineers at the bio-inspired robotics lab at the University of Cambridge are researching how to create robots that are soft, like us. And by choosing the right materials, they've created an artificial hand capable of bringing music to life, almost like a classical sonata. Maybe I raised the bar a little too high, though. I should explain, for demonstration, our robotic hand is only using one finger to play, kind of like you would when you're first learning. If you recognise it, it's Twinkle Twinkle Little Star. Huijiang Wang is investigating the development of fleshy soft robotics that can confer emotion. That makes sense if robots are to become a greater part of our day-to-day lives. Their evolution should result in safe physical forms. But not all robots will fall into that subset, and when you get into defining robotics, it's no easy task, as Huijiang and I discovered. What do you think defines something as being a robot?
I think a robot is something like a tool that can replace human beings in performing some manipulation tasks.
Do you think a robot has to perform a physical task, so manipulation of something in the real world, to be classified as a robot?
That is one branch of robots. It can be a more general definition. For example, it can also be virtual.
Perhaps then the definition of a robot is something that will carry out a task, and it might not be in the physical realm, it might be digital, but there's some kind of control strategy in place that means that that robot is doing something at the right time rather than just responding to its environment intuitively.
Yes, that's true.
You can see robotics as a difficult discipline to define. When we think of the future, we think of AI, digitization, humanoid circuit boards and autonomous cars. But maybe if we stick with the idea of a traditional robot, it's hardware. Maybe we're already in the midst of a utopian robotic future. It's time to take a look at a handful of examples where programmable robotics is helping us excel, from deep in the Weddell Sea to in the hands of a surgeon.
And we'll meet one such robotic surgeon in just a moment.
First, though, Tricia mentioned there the Weddell Sea, which is off of Antarctica. This is actually one of the locations that the now infamously named Boaty McBoatface, which is an autonomous underwater vehicle, has visited. Boaty is one of actually a fleet of robots that are cared for by Martin Furlong. He's at the National Oceanography Centre. Martin, for the uninitiated, Boaty McBoatface, what is it? What does it look like?
Well, Chris, it's a basically a little yellow submarine. It's about 3.5 meters long, weighs about 750 kilos. It's got a propeller at the back, some control planes. It's got little stubby wings, which allows it to go up and down through the water column. It's designed to go a really long way, so it's sort of like thousands of kilometers and many months endurance. But its primary purpose is actually just to carry sensors. So we view these things as sensor taxis, and you can fit whatever sensors you need for a specific science campaign that the vehicle's working on.
Thousands of kilometres. That's a lot. How is it powered?
So it's basically battery powered. So it has a whole set of they're lithium thionyl chloride. So these are lithium batteries, which are single-use batteries. We also have some rechargeable sets in there as well. And what it does is it goes very slowly, so it doesn't use very much energy for propulsion. And we run low power sensors on there, but it has a very big battery pack. So it's got the sort of same amount of energy that you'd get in for example, a Nissan Leaf.
And so for robots like this, underwater robots like this, what is their main aim? Why have you got them?
So they're basically a generic tool for supporting the oceanographic community. So there's a whole fleet of different marine robots, which we actually run at the Oceanography Centre. Boaty is just one. And they're used, as I said, to basically to carry sensors to different parts of the ocean to actually understand what's happening in that specific location. Whereas on terrestrial planes, you can use satellites to get huge areas and visualize huge areas of the globe. Because of the properties of seawater, you basically have to move your sensors to the specific location you want to measure. So all of these vehicles are there to basically take measurements of the ocean. And it depends on the sort of science which is being undertaken. So some of it is looking at the structure of the water column, others looking at actually what's happening on the seabed and like the geology. And other things are looking at sort of like the biology that's there. So whether it's like big marine animals, or whether you're looking in the deep ocean and you're looking at some of the effectively the creatures which are on the bottom of the abyssal plain, so like 4,000 meters down.
Do they follow a pre-programmed mission, or do they actually make decisions for themselves, these craft?
So this depends on the vehicles. So generally they will follow a pre-programmed mission. So for example, Boaty, is designed to go a very long way, but what it's actually composed of is a lot of short little missions. So we will tell it to go and do a little mission. So it will dive down, it will go and do a survey, it will come to the surface, and then it will talk to us via satellite and ask us what it wants to do, what we want it to do next. And so you can stitch all of these little missions together. But during the actual mission, it's operating completely independently. So it will be taking sort of measurements of its environment to try and avoid bumping into things and make sure it doesn't get lost. And then it will come back to the surface. I mean, other vehicles that we have are less autonomous. So you have remotely operated vehicles, and these are sort of controlled from a ship, typically down a long cable to a robot, which is on the effectively bottom end of a wire. People are also looking at effectively surface vessels, and these are uncrewed surface vessels, and they would be controlled from shore typically. And so there were people working on the situations where you'll have a control station running an uncrewed surface vessel, somewhere in the ocean, and then that will be deploying an ROV that you can control remotely from shore. So you will effectively see what's happening at the bottom of the ocean and be able to manipulate the bottom of the ocean like thousands of kilometers from shore, remotely from a shore station.
What can we do with these things, though, that we couldn't do before? Do they actually unlock new realms to us or for us, or is it just a question of it's more practical to operate this way?
So they have some unique capabilities. So you mentioned sort of like Boaty being in Antarctica. So it's currently on a campaign to look at the Thwaites Glacier, and it will be going sort of tens of kilometers in from the ice front. So effectively there's a big ice glacier floating on the Amundsen Sea, and Boaty will basically go from the front of the ice, so 20, 30, 40 kilometers in, studying what's happening underneath it. So you could do that with a manned submarine, but it'd be incredibly dangerous and incredibly expensive. Also, there are other systems. So there's an array of robotic floats in the ocean. These measure effectively the structure of the ocean and the deep ocean, and there's like 4,000 of them sending back data, which allows you to run ocean models and sort of predict impacts of climate change. So you could technically do this with ships, but it's just so much more efficient to do it with robots.
It's good to hear there are all those advantages. So we're pushing the boundaries and boldly going where no unmanned autonomous vehicle has been before. Martin, thank you very much indeed for telling us all about it. That's Martin Furlong, who is the caretaker for Boaty McBoatface, among others.
Now, from submarines to surgery, and that might not at first glance sound like a logical link, but at the end of the day, in both cases, you have someone sitting in front of a screen controlling robotic arms from a distance. And when it comes to medicine, this is becoming very big business. The venture we're about to hear from are industry unicorns. These are start-up companies that have been valued at over $1 billion. Thanks to their technology that can make the benefits of keyhole surgery available to everyone who needs it. As we'll find out, Tricia Smith reports.
I'm at CMR Surgical, which is a medical robotics company based in Cambridge, and I'm here to have a demo of and have a look around the Versius system, which is a medical robot that assists surgeons in performing laparoscopic surgery. So hopefully I don't break anything.
Too right, Trish. Before she manages to get her mitts on any of the tech, though, Trish did speak with co-founder of CMR Surgical, Mark Slack.
What's the difference between normal laparoscopic surgery and that where you've got a robot assisting you?
Normal laparoscopic surgery is keyhole surgery, and that's doing your surgery through tiny little holes. Now, there's huge advantages of keyhole surgery over open surgery. To give you one statistic, you reduce surgical complications by 50% doing exactly the same operation by keyhole rather than by open surgery. However, in the world, only about 30 to 40% of people who could have keyhole surgery do get it. And the reason for that is it's really difficult to do. If you bring in robotic keyhole surgery, the end of the instrument is articulated, so it behaves like a hand, like a wrist. In conventional keyhole surgery, the slang term for it is straight stick surgery, because the instruments have no articulation, and that makes it incredibly difficult to do. That's where the difficulty comes.
What's different about the Versia system compared to other robot-assisted laparoscopic devices?
We've got a very different design from the other ones. That makes us able to have a smaller robot. It's able to be placed more efficiently around the table. We can get better reach, and that just widens the scope of what we can do. So we can do surgery everywhere from the chest to anywhere in the abdomen.
Is there anything that's automatic, or does the surgeon have complete control over everything?
You know, if I had a person standing next to the table and they wanted to get close to do something, they can push the arm across, and I won't know that the arm's been moved because it adjusts automatically, and the tip where it's working and what it's doing stays exactly where it was.
And the tip staying exactly where it was is important because the surgeon needs to have complete control over what's happening in the patient.
The word is precision. That's what you want. You know, you want absolute accuracy and precision in surgery, and that's what the robot gives us.
Yeah, it's time to get up close and personal with the equipment. And Tricia got that chance, to play surgeon with implementation executive Mario Bento.
The system consists of the Vertius console, which is the brain of the system, and consists of 4 Vertius arms. So the console itself is where the surgeon would sit or stand.
And attached to this rolling brain of the operation, which has a very large screen, if you remember the nunchuck attachment to an original Wii, it basically looks like there are 2 little nunchucks which have joysticks and a couple of buttons attached to these arms that then have a freedom to move around. And I'm assuming that that's how the surgeon then operates the robotic arms.
Yes, so as we can see, when the console is turned on, the controllers actually float, so they float in the air. Also, there's just enough space between where the surgeon sits to where the screen actually is, which maximizes that 3D view that the console has. So we'll always need your 3D glasses to actually see the 3D screen, of course.
Oh gosh, that's amazing. I'm leaning forwards and backwards and I'm looking at this screen, and the field of view is getting closer and further away, but it's definitely 3-dimensional.
The controllers themselves, they have 3 sensors on each controller that detect someone's hand. So it's a safety feature of the robot itself. So it knows if I am holding the controller appropriately, it allows me to use the instrument. But as soon as I let go, or if it doesn't recognize my hands, if I'm not holding it properly, it won't let me move the instruments.
Okay, so I have to hold these joysticks to engage so I'm allowed to move. I press a button with my thumb that says, yes, start using this arm. And then if I press my first finger, it's kind of like the trigger on a joystick, and I can close and open the instruments. And hopefully I won't collide with anything.
So
There we go, I've gone wrong. I've got something flashing on the screen in front of me, and also the robotic arm by the operating table is flashing too.
It's not to worry, Mario got the kit up and running again eventually, but Tricia thought she would leave the robotics with the professionals. Just enough time though to revisit Mark and discuss her experience.
I had a go. I wasn't very good, I have to say. But one thing I noticed was how ergonomic the setup is when you're operating, and the support that you have, and the fact that you can let go and everything pauses. It's like pausing a video game. So why is that important in terms of the safety to the patient, and also in terms of the comfort and the safety to the surgeon?
You know, there are multiple sides to that. So fatigue doing normal keyhole surgery means that you're struggling and you're probably more prone to make errors. There's a little known fact that many senior surgeons get a lot of musculoskeletal difficulty from operating. That's one big area. A lot of the instruments that are made are too big for a woman surgeon to use because their hands tend to be smaller. And those are all things that the robot can help overcome. So we pay a lot of attention to the ergonomic. I don't want to see surgeons being injured and then having to curtail their careers because of neck problems. So we see that as a very important part of the program. So they are more rested while they're operating, which means better outcomes, and they remain able to operate for longer.
Do you think that in the future we're going to have fully autonomous robotic surgeons?
I don't think in our lifetime. But what I do see the robot introduces a system between the surgeon and the patient. And that allows us to do all sorts of other exciting things. So we can actually standardize surgery. We can put checklists onto it. Every time the arm moves, the computer is registering its movements. Every hand movement of the surgeon is measured as well. And we're starting to correlate that with outcomes. When you go and have your operation, wouldn't it be nice to know how good your surgeon is?
So these robots not only are tools that allow us to access the body in a minimally invasive manner, they also give feedback that wouldn't otherwise be recorded if you did manual laparoscopy.
And all the data that is got through there, when you talk about AI and things like that, that's where we are going to mine a lot of data. And potentially we will come to a point where it can warn you that you're about to make a mistake. So those are the sort of things that I'm looking towards as being futuristic.
Tricia Smith speaking to Mark Slack and Mario Bento from CMR Surgical there. We're discussing some of the novel ways robots are pushing the boundaries of human endeavour.
We've heard about these machines in far-off oceans and others in the operating theatre, but what about robots that can come home with us? Researchers at Northern Arizona University have developed a robotic ankle exoskeleton that doesn't just help get you up the stairs if you have an ankle injury, it could also be fundamental to your rehabilitation too. Tricia has hot-footed it from the robotic operating theatre to talk to Zach Lerner to hear how it works.
It's really easy to make a wearable robot that makes walking more difficult. It's much harder to make a wearable robot that makes walking easier. What I mean by that is when you add something to the body, when you add heavy motors and batteries, it can actually be detrimental, especially if you place them on the feet or the lower legs. It's really metabolically expensive. It takes a lot of energy to move heavy limbs.
So with the wearable exoskeleton that you've developed, can you explain to me what it looks like and how it works?
So we've designed our ankle exoskeleton in such a way where the heaviest components are located close to the waist, like a location where you would carry a fanny pack. And then we have cables that travel down the leg and they actuate pulleys on an ankle assembly. There's a foot plate and a calf cuff and this rotary joint that's actuated by these cables, and it's driving the foot in a particular direction.
What's the difference between using the exoskeletons for rehabilitation and also using it for assistance?
The device can be controlled to provide torque or forces that interact with the body that work in conjunction with the muscles. But the reality is that no one wants to wear a leg brace for the rest of their lives. So we've been developing a technique where we actually provide resistance to the body at a particular point in the gait cycle. And so it's training muscles to turn on at a particular time when it's most beneficial to efficient walking.
So by using these exoskeletons in resistive mode, without wearing it, their gait is improved.
That's exactly right. It's been really remarkable how quickly our participants in our clinical research studies have improved. So in as little as 10 sessions over 4 weeks, we've seen a remarkable improvement in their walking speed, in their walking pattern. We can actually make people better. We can improve their underlying function, even when they're not using the device. And it's really exciting to think about devices that can go home with individuals and can be used daily for functional training, and to allow a connection between a physical therapist who could remotely monitor their patient's progress by just using the onboard sensors that are embedded into these devices.
And when these devices are working in assistive mode, how do you make that device able to adapt to a changing environment?
So the approach that we've taken is to embed force sensors under the forefoot, and this allows us to approximate what the calf muscles are trying to achieve, and using this as a proxy measure for someone's intention. And these sensors can capture when someone is naturally speeding up or slowing down or walking on stairs or a ramp. And it's also important that we have control strategies that are able to adapt to different gait patterns. They're able to adapt to different neurological conditions, different people using the device. In some ways, the mechanical design of a wearable robot is the easy part, the control of the device can sometimes be much more difficult.
What do you see exoskeleton technology looking like in the future with advances?
We're going through a really remarkable period of electrification of personal mobility. So electric skateboards, electric scooters, and in the wearable robotics space, we're electrifying joints. And we're benefiting from the proliferation of affordable batteries and improvements in battery capacity, the large-scale productions of appropriately sized motors. And so as the wearable robotics space grows in conjunction with electrified mobility, we'll see the benefits of devices that are more affordable and more effective because they're smaller, they're lighter, and they can be used for a longer period.
Zach Lerner there, speaking with Tricia Smith.
Hasn't it been impressive to see what robots are up to all over the world? It almost feels like there can't be any more advancements, but of course there will be. Jonathan Rossiter is here to talk to us about them. He's a professor of robotics at Bristol University, and he believes that one day we'll scrap the word robot entirely for the term artificial organisms. Jonathan, start us off by saying, what actually is an artificial organism?
I think there have been many preconceptions in robotics. People have a look at science fiction and maybe they see their robot vacuum cleaner that's moving around their homes. So they think of robots maybe as conventional, made out of metal and plastics and so on. And that's great. And we make 10 million of those around the world. And that's wonderful. But if you look at organisms in nature, they have really exciting properties which are really quite similar to robots. So we can think of robots more in the lines of an organism.
Right, and where does this feature and where does it end? You know, is there at all a chance that these robots, if we're starting to term them like organisms, might be feeding and getting energy from similar places that we do?
Yeah, if you think of a robot has got a body made out of plastic and metal, and it's got a battery where really it's where it gets energy from. And then it's got a brain which is made out of a silicon chip or a computer. Whereas artificial organisms, the kind of thing that we work on in Bristol, they have a stomach which eats biological food, it eats energy, gets energy from food. It's got a body which is soft and compliant like a normal organism, and it's got a brain which is much more like a biological brain. Now, one of the really interesting things about these robots is that we can make them out of materials which are soft and compliant and that can biodegrade safely into the environment. And that changes the way in which you make the robots and the way in which you can use them.
How exactly do those artificial stomachs work? How do they transfer the energy from inside the stomach to the robot?
One of the challenges in making an artificial stomach is that you have food, which is chemical energy. We need to turn it into electrical energy. One way to do that is to employ something which is naturally occurring in the environment, which is microbes. So the microbes can eat the food for us, and then they generate electrons and protons, the important parts of electricity. They break it down into those two components, and then we use those electrons in our circuit, in our robot.
So when we're speaking of these soft robots, what materials are you using?
Yeah, one of the examples I use is a kind of like a gummy bear robot, a robot that's made out of a jelly-like material, a kind of material that you might get in candy and sweets. And that's got some really interesting properties where when you pass electricity through it, it can do something interesting. It moves a little bit like a muscle. Now, once you've made a robot out of that, it can move on its own. And then at the end of its life, because it's a little bit like a gummy bear, it can biodegrade to nothing. Microbes in the environment will eat the robot and it'll be safe.
So we've heard, Jonathan, about how robots are going off to carry out difficult bits of difficult tasks that we can't handle. What is the purpose of having something that's biodegradable? Why is that useful to us?
One of the challenges with current robots is that you can make 10 of them and 100 of them, and you can put them out into the environment, like in the Atlantic Ocean, to monitor the sea there. But at the end of their life, you've got to bring them back. You've got to track them and capture them and bring them back. Otherwise, they pollute the environment. With a biodegradable robot, you can deploy hundreds, thousands, millions, billions, trillions of these robots. And they'll do something really useful. They'll monitor the environment. And when they reach the end of their lives, you don't have to bring them back. You just leave them to degrade. And they can have a net positive impact on the environment. And that's something we really find very difficult to do with conventional robots.
I mean, it sounds fantastic, Jonathan, and something that you'd never consider when you're talking about electrical items or things that we're using for tools to go out and find us information. There must be quite a few challenges creating biodegradable robots, because I can't imagine that the technology's there before you. You know, this is something very novel. What are those challenges?
Yeah, so we have to make those three components: the body, the brain, and the stomach. And they each have their own challenges. The body, we have to make these muscles, these artificial muscles, which are effective. They've got to be as strong as our biological muscles. The stomach has got to be as effective as our stomach at turning food energy, which is incredibly rich in energy, into movement, as it were. And the computational side, we want to make computers and artificial intelligence for these robots, which isn't made out of the kind of thing you can find in your mobile phone, a piece of a silicon chip, because that doesn't biodegrade very well. So we have to look at those technologies. And we're doing a lot of work in this. And I think maybe in 5 or 10 years' time, we can show the kind of first examples of these technologies.
Well, that's a good question looking towards the future. In 5 to 10 years' time, or perhaps looking past that as well in a few decades, where do you see the field of robotics going? I know that through speaking in this last half hour, we all know that robotics is such a big field, but where in particular do you think those advancements lie?
I don't think there's any limit, actually, to where the robots will be. I term future robots as ubiquitous, and it's probably going to be the case that we don't even refer to them as robots, because they will be around us, they'll be with us, they'll be on us as part of our clothing, for example. They will be inside us as food that we eat, that'll be robotic, and our organs inside, when they go wrong, will be replaced by robotic organisms. And so really our lives and our future are very much entwined with these new style of robots.
Is there an example? Is there a piece that's sitting in your lab at the moment that you can describe to us and what the function might be for it?
So at the moment, we're working on edible robots, and that is robotic food. And you think, well, hold on, if I've got a plate of spaghetti, why would I ever want it to be robotic? Well, there are several reasons. If you have a young child, for example, who doesn't like to eat their food, if the food is more entertaining on the plate, perhaps that's going to encourage them to eat it. So that's like a trivial, but actually quite important example. And now the even more important, pressing example is people who've had a stroke, for example, and they can't swallow very well. What happens if your robotic food would swallow itself into your stomach? So you put it in your mouth and it would worm its way into your stomach. So there you have the pleasure of eating. You don't have to eat some horrible thinned down liquid, and the food will deliver nutrients exactly where it's needed. So that's the work we're developing at the moment. And we think this is going to take a bit of time, but it's really exciting.
Thanks there to Jonathan Rossiter.
I'm terrified by the prospect of who's eating who.
And there you have it. Robots making waves in the Weddell Sea, operating theatres and the staircase. I get the impression, though, there's plenty more to come in 2022.
Well, from robots to our question of the week. To finish this week, we're going to hand over the reins to you, of course. Let's see who's been in touch to ask Naked Scientist Otis Kingsman for his help.
Hello, I'm Patrick from San Francisco. My question is, when I have cold feet, why won't my brain let me sleep?
You're not the only one wondering about this, Patrick. With winter weather at full intensity, I know this feeling of cold feet during sleep all too well, and it certainly keeps me up at night. Fortunately, I know exactly who can help us.
I'm Professor Guy Leshtoner. I'm a professor of neurology and sleep medicine. I'm not sure if there's any more scientific an answer apart from the fact that you need to be comfortable when you get off to sleep. And clearly, if your feet are cold, then that's not particularly conducive to being comfortable, and it's therefore not particularly conducive to falling asleep.
If we're not comfortable, our brains think something is or is going to go wrong while our bodies aren't conscious to stop it. Professor Guy explains there are other ways, though, that temperature can affect our comfort.
We know that when you drift off to sleep, actually the temperature difference between your core temperature and your peripheral temperature changes, so the differential increases, and this is thought to be part of the process of falling to sleep. Your body temperature is important when it comes to dreaming sleep, because during dreaming sleep, or REM sleep, rapid eye movement sleep, we lose the ability to regulate our own body temperature. And therefore, this is potentially quite a dangerous thing for us to do. If our body temperature is too low, then actually the brain prevents itself from going into REM sleep or dreaming sleep, because otherwise there is a risk that our body temperature would drop too low to allow us to continue living.
Yikes. Our bodies certainly do not like being cold. But according to Guy, the same thing happens on the opposite end of the temperature spectrum.
Actually, occasionally people feel that their feet are too hot to enable them to sleep. And this is something that is very common in a condition called restless leg syndrome. Typically, people with restless leg syndrome will say that they feel an urge to move or a discomfort. But that sometimes manifests as a feeling of heat, and people will search out cold parts of the bed in order to obtain a degree of comfort.
So, Patrick, based on the science, getting to sleep all comes down to general comfort. If you're cold during winter nights, turn up the heating, snuggle under a warm duvet, and wear clothes that keep your body temperature warm. Next week, we'll be shining a light upon this question from listener Michael.
What makes stars twinkle, and what can their colors tell us about them?
And you can get in on the debate on our forum. That's nakedscientist.com/forum. You can also email your questions or solutions to chris@thenakedscientist.com.
That's it for this week, but we'll be here at the same time, in the same place, next week, sticking our noses into the lasting effect COVID has had on our senses of taste and smell. Some people out there are suffering more than others. It's definitely not to be missed. A special mention to all of our guests that featured on the show today, and a thanks to Tricia Smith, who put the show together. The Naked Scientists come to you from the University of Cambridge's Institute of Continuing Education. It's supported by Rolls-Royce. I'm Harry Lewis. Thanks for listening, and until next time, goodbye.